A train weighing thousands of tons is racing forward at 100 miles per hour. Then, without warning, the engine fails. No power, no braking assist, just pure momentum and steel. What happens in the next 10 seconds decides whether everyone on board walks away or whether this becomes a headline. Today, we're breaking down exactly what happens when a train engine fails at full speed, and why modern trains are built to survive the one moment they're never supposed to face. When a locomotive engine fails at 100 miles per hour, the crew doesn't get a warning light and time to think. It happens in milliseconds. Modern locomotives run on a dead man's safety system. If the engineer loses control or the engine cuts out, sensors detect the loss of power instantly. The train doesn't just coast. Automatic systems immediately shift into what's called emergency propulsion cutoff. The drivetrain disconnects so a failing engine doesn't drag the wheels or cause a derailment from mechanical shock. But here's the terrifying part. Momentum doesn't care that the engine died. A train at 100 miles per hour carries the kinetic energy of a small explosion. Even with zero power, it can keep moving under its own weight for over a mile before natural friction and air resistance alone would stop it. That's why engine failure is dangerous, not because the train stops too fast, but because it doesn't stop fast enough on its own. You'd think the obvious fix is simple. Hit the brakes hard, right now. But full emergency braking at 100 miles per hour is its own crisis. Trains are incredibly long and incredibly heavy, and unlike a car, every train has slack between couplers connecting each car. Slam the brakes too aggressively, and that slack snaps taut all at once, sending a violent shock wave down the length of the train. This is called stringlining, and it's caused real derailments throughout railway history. So instead, when an engine fails, the system doesn't panic. It calculates. Modern trains use pneumatic braking systems that apply pressure gradually and evenly across every single car simultaneously, using compressed air lines running the entire length of the train. It's designed so the front car and the back car brake in near-perfect sync, treating the whole train as one unit instead of a chain of separate objects fighting each other. This is the difference between a controlled stop and a catastrophic pileup. While all this is happening automatically, the engineer isn't just sitting there. Within seconds, they're trained to do three things: confirm the failure isn't a false sensor reading, communicate the emergency down the line to dispatch and any nearby trains, and manually engage backup braking if the automated system hasn't already. This is why train engineers train for failure scenarios, not just normal operation. Simulators specifically recreate engine failure at speed because muscle memory in the first 5 seconds is what actually saves lives, not decision-making. There's no time to think. There's only time to execute what's already been drilled. And there's a detail most people don't know. Many modern locomotives have redundant engines, a secondary power unit that can take over specific critical functions like braking assistance and lighting, even if the main engine is completely dead. It's the train equivalent of a plane's backup hydraulic system. Here's the twist most people don't expect. The danger of an engine failure has less to do with the failure itself, and everything to do with what's on the track ahead. A straight, clear track at 100 miles per hour with an engine failure is almost always survivable. The train simply glides to a stop over roughly a mile or two. But if that failure happens approaching a sharp curve, a junction, or, worst case, another train on the same line, the outcome changes entirely. This is why railway systems worldwide invest so heavily in positive train control. Networks of sensors that automatically detect a disabled train and alert every other train and signal box in the area within seconds. It's not just about stopping the failed train safely. It's about making sure nothing else on the track collides with it while it's rolling to a stop. Engine failures at speed aren't rare hypotheticals. They happen. And in the overwhelming majority of documented cases across modern rail networks, trains have come to a full, controlled stop without derailment or collision. That's not luck. That's decades of engineering specifically designed around the worst-case scenario. Because railway engineers don't ask, what if this fails? They ask, when this fails, what happens next? And they build backwards from there. So next time you're on a train doing 100 miles per hour, know this: if the engine failed right now, you're not in the chaos you'd expect. You're inside one of the most over-engineered safety systems in modern transportation. Would you trust this system with your life? Comment yes or no below. I want to see what you think. And if this blew your mind, hit subscribe. Because next week we're breaking down what happens when a plane loses both engines mid-flight. You don't want to miss that one.